Okay, so good day. So for this video, I'll be discussing about the procedure on the computation of the nominal moment strength M sub n. So again, so from the previous videos or lectures that we had, so we had identified three things, okay? So from previous discussion, number one is we were able to check the compactness of the section. Okay, so we were able to identify whether the section is compact, non-compact, and slender elements, yung tatlong classification ng section. So that's the first one that we had before. The second thing that we discussed before is the lateral support conditions. Okay, so how do we check the lateral support condition of the beam? That is by comparing the LB versus the LP and the LR. So through that comparison, we would identify whether the beam is laterally supported, partially supported, or laterally unsupported. Okay, so that is the lateral support condition. Then yung pangatlong na-identify natin last time is yung determination ng CB. Again, what is CB? CB is the gradient moment multiplier. So we could solve for the C sub B using the given formula wherein we will be needing the Mmax, the MA, the MB, and the MC, if you could still recall. Okay, so yung tatlong to, compactness, lateral support condition, tsaka CB, ito yung tatlong kailangan natin na kailangan nating information para tayo makapag-compute ng nominal moment strength M sub n. Again, bakit kailangan natin yung M sub n ulit? Ito yung para ma-identify natin yung para ma-identify natin yung magiging design strength ng beam natin. Kasi ang design strength is just the phi, which is 0.9 times Mn. Okay. So this will be the procedure for the computation of the Mn, and this is applicable for eye and channel shape sections bent about their major axis. Okay, so take note. Major axis to, no? Okay, so first step is yun nga. First step is check the compactness of the section. So yun yung una natin ginawa. Classify the section whether compact, non-compact, or slender by comparing the lambda versus the lambda p and the lambda r. So we have that we did that before. Then yung second step is kapag yung section nalaman mo siyang compact section, so doon ka pupunta sa step 2. Next is to check for lateral torsional buckling or LTB kung mangyayari by checking the lateral support condition. So you just have to check the LB versus the LP and the LR. So yan yung ginawa rin natin from previous lecture. And by comparing LB with LP, you could identify whether the beam is lateral supported. Pagka lateral supported, ibig sabihin, walang lateral torsional buckling na mangyayari. Therefore, the Mn could be simply equal to the moment plastic, which would be equal to Fy times Z. So alam nyo na kung paano mag-solve ng Z, right? So makukuha mo na yung Mn. Again, kapag lateral supported, tas compact yung section, yan yung magiging Mn natin. Fy times Z. Okay, so tapos na tayo dyan pag ganyang case. Now, ang second case natin is yung 2.b. That is kapag yung LB mo is greater than LP but less than LR, so the beam would be partially supported. Naalala niyo yung discussion ko doon sa partially supported? Yung na graph. So ano yung graph kapag partially supported? Diba linear na decreasing? Okay, so ibig sabihin, the Mn decreases linearly as the LB increases or approaches LR. Diba? And yung Mn equation na yan would be given by this equation. Okay? So as you can see from the given formula, okay, that is linear. First degree lang. Kaya nga yung graph natin doon is linear. Okay? So ito yung gagamitin mong formula pagkuha ng Mn kapag partially supported yung beam. That would be CB multiplied by Okay, so yung CB na-discuss ko na sa inyo from previous presentation kung paano paggawa ng CB times MP. Ano yung MP? Yung MP is Fy times Z minus MP 0.7 FYSX tapos LB minus LP, LR minus LP. Then that MN calculated should be less than or equal to the limit, and the limit natin would be the MP. So I hope you still remember how to identify and solve those variables that are involved in the given equation. Okay? So yan yung magiging MN natin kapag partially supported. Again, yung CB is the moment gradient multiplier or the lateral torsional backing modification factor. Okay, so next case. Paano naman yung case 2.c? This is applicable kapag LB is greater than LR. That means the beam is laterally unsupported. Pagka laterally unsupported yung beam, 'di ba? Pagka laterally unsupported yung beam, ibig sabihin gumigiwang siyang ganyan. So therefore, there will be an elastic LTB or lateral torsional buckling occurring on the beam. So syempre, nangyayari sa kanya yung ganyan, yung LTB. Therefore, yung MN na gagamitin mo sa kanya would be this one. FCR times SX. Ano yung FCR? Oh, ito yung formula ng FCR. Oh, familiar naman lahat tayo sa mga variable, no? Yung CB, the LB, the RTS, the torsional constant K, we have the C, the SX, the HO, lahat. Ibig sabihin, lahat yan na-discuss ko na from previous lecture. So, direct substitution lang yan. You could solve for the FCR. I-times mo na SX, yun ay MN. But you have to check that FCR times SX with the limit. Again, ang limit natin would be MP. Ano yung MP uli? Baka nakakalimutan. MP is equal to Fy times ZX. Ayan. So, nakadefine naman dyan yung ibang mga variables like the E, okay, the E, the J, the SX, or the HO. Okay. So, yon ay the case applicable for non-compact sections lahat yon. Yung 2A, 2B, 2C. Lahat sila applicable for compact section. Etong case 3, okay, yung number 3 naman natin dito, this is applicable for non-compact section. Non-compact na. Okay. So, diba, malalaman mo kung ano yung compactness. Pagka compact yung section, dun ka sa case 2. Case 2A, 2B, 2C. Pagka non-compact yung section, dito ka natatalon sa step 3. Step 3 na for non-compact section. Okay. O, susundan mo lang. Pagka non-compact section daw, yung MN mo would be the smaller between this 3A at saka 3B. Okay. Sa 3A, i-check natin siya kasi non-compact yung section eh. Pagka yung non-compact yung section, ang ibig sabihin nun, it's either the flange, diba? Yung flange, yung non-compact, o kaya yung web, yung non-compact, diba? Kasi sinek natin yung compactness nila separately. So, pagka yung flange, non-compact, pwede magkaroon siya ng flange local buckling failure. Kapag yung web, non-compact, pwede siya magkaroon naman siya ng web local buckling. So, we will be checking that if that will happen based from these following conditions. O, tingnan nyo yung 3A. Yung 3A is the check for flange local buckling. So, i-check mo yung lambda value mo. If it is less than lambda P, there will be no FLB. Again, if lambda mo is greater than LP but less than LR, so you have a non-compact flange. So, therefore, merong flange local buckling. So, ito ngayon yung magiging equation mo for MN pagka ganun yung condition ng beam mo. So, mahaba lang yung empirical equation pero yan yung magiging MN natin. Okay. Tapos, kung hindi ka man masatisfied dun sa 3A, doon ka pupunta sa 3B naman. Okay. Yung 3B naman is for lateral torsional buckling. So, i-check mo yung lateral support condition niya. I-check mo kung laterally supported ba yung beam mo, partially supported, o kaya laterally supported. Pagka laterally supported, okay, so ang MN mo rito is equal to MP, no? Which is equal to Fy times Zx. Okay? Pagka partially supported naman, ito naman yung gagamitin mong MN formula. Pagka laterally unsupported naman, ito naman yung gagamitin mong formula for MN. So, these are actually the procedure. Okay? So, susundin mo lang 'yan. So, even sa board exam, if ever lumalabas 'to sa board exam, ah, naka-copy paste yung provision from the NSCP, ibinibigay dun sa problem. So, naka-copy paste siya. So, kumbaga given lahat ng mga formulas na 'yan. So, nasa sa inyo lang, you should know how to use these formulas lang to solve for a certain problem. So, magiging useless kahit open notes pa 'yan, open formula sa exam kung hindi niyo naiintindihan kung paano gamitin. So, that's why iniisa-isa ko step by step. Okay? So, para maintindihan niyo kung ano yung mga provisions na 'to. Okay, so these are the procedures. So, step 1, compactness check. Yung step 2 for compact section, 'di ba? Step 2 is for compact section. Then step 3 is for non-compact section naman. Okay, so from there, ultimately, kailangan natin ma-solve yung MN. Tapos i-multiply mo ng phi, di yun na yung design strength should be greater than MU. So yan yung LRFD principle natin. Okay? So let's try to have example to apply this procedure. Okay. So for this sample problem number 5, we have a simply supported beam subjected to a uniform service dead load including the weight of the beam, a uniform service live load, and a concentrated service dead load are shown. Okay, so given na yung uniform loads dead tsaka live, at tsaka meron tayong concentrated na dead. Okay, so these are the loads on the beam. So take note that the concentrated load of 200 kilonewton is not applied at the midspan. Wala sa midspan. The beam, okay, the beam has continuous lateral support and A572 grade 50 steel is used. Anong ibig sabihin ng statement that the beam has continuous lateral support? So anong ibig sabihin ng statement na yan? Okay. So ang ibig sabihin ng statement na yan, the beam is considered as laterally supported na siya antemano. Ibig sabihin, hindi mo na kailangan i-check yung lateral support condition, yung LB, LR, tsaka LP. Hindi mo na kailangan gawin yun. Kasi nasa statement ng problem na continuous lateral support daw siya. Ibig sabihin, lateral supported siya. Ibig sabihin, hindi siya magkakaroon ng lateral displacement. That would be possible in the actual scenario kapag yung steel beam mo is nakadikit sa slab. Diba? Ito yung beam mo. Tapos may slab dito sa side na to. Tapos may slab din dun sa kabilang side. So, ibig sabihin, yung beam mo na naiipit siya ng slab. Kapag ganun yung scenario mo sa construction or sa design mo, the beam can be assumed to be laterally supported all throughout its span. Okay? Kasi yung slab serves as a lateral support all throughout the span. So, ganun yung nangyayari sa actual design. Okay, so the steel is of grade 50. So, FY niya 50 KSI. Then, we are asked to check for the adequacy of this size, W30 by 116 for this beam. Okay, check adequacy. So basically, we will check it first sa flexure kasi sa flexure pa lang tayo. Later on, we could check it against shear at saka deflection din. Okay, so for the meantime, for flexure muna. Okay, so these are the given and these are the properties of the section which were taken from the manual. Okay. Okay. So basically, to give you a background on the solution of this problem, okay? So basically, ang magiging solution natin dyan would be, so check adequacy. So solution for problem number 5. Okay? Solution to problem number, tama ba? Okay, problem number 5. Okay, so para natin ma-check yung adequacy, what we're going to do is, so dapat yung design strength niya should be greater than or equal to MU. Okay, so unahin natin muna yung MU. So what is MU? So i-check natin kung greater than. So yan yung question mark. Okay, what is MU? MU is the maximum ultimate moment sa beam, on beam. Diba yung beam natin, so simple beam, tapos may uniform load. Okay, so yung uniform load, say WU, gamitan mo siya na 1.2 given yung dead load plus 1.6 given yung live load. So makukuha mo yung WU. Ayan, so yan yung WU. Tapos, meron tayong concentrated load sa wala sa gitna. So isolve mo yung PU. Yung PU is, ano ba yung given na load? The given na load is concentrated service dead load. Okay, service dead load daw. So for 8 meter. So that would be dead load kaya 1.4 of the given dead load. So makukuha mo yung PU dyan. Dito makukuha mo yung WU. Okay, pag alam mo na yung PU tsaka WU, kaya mo ma-solve yung reaction sa A, kaya mo ma-solve yung reaction sa B. Okay, so statics lang. So from there, identify mo yung maximum shear. Kasi from the shear diagram, you could identify the maximum moment. Okay, so yun yung kailangan mong identify yung maximum moment. Halimbawa, sa shear, so tataas ka, you go up by RA, tapos bababa ka ng uniform load, tapos bababa ka ng PU, tapos uniform load uli, tapos tsaka yung RB. So basically, ganyan yung mag-itsura ng shear diagram mo, no? Pag na-drawing mo na yung shear diagram, you could now do the moment diagram. So the moment at A is 0, tapos yung moment dito would be equal to the, kasi first degree to eh. This would be second degree. Decreasing shear, decreasing slope. So pag ganun. So second degree. Tapos yung trapezoid naman, ganun ulit. So you need to identify the magnitude of this. And this would give you the MU maximum. So yan yung aalamin natin. So yung MU maximum na yan, eto yan. Ito yung MU maximum. That is the maximum moment dun sa moment diagram. Okay, so hindi ko na ipapakita yung detalye. So nirarun ko lang yung paano maging solution. Okay, so pag alam mo na yung MU, next part na gagawin natin is to check yung phi MN. So yung phi MN. So paano mo masasolve yan? Again, yung phi natin is 0.9 kasi flexure. Now, the question is, ano yung MN? Okay, so sabi natin, given yung, so unang gagawin natin dito is check compactness. Check compactness. Okay, so paano yun? So you solve for lambda, tapos i-compare mo siya sa lambda P at saka lambda R. Okay? Pero since the section given in this problem is a standard wide flange section, most likely it would be a compact section. Okay, so again, if you are in doubt, no, and if you don't know, you don't have the formula to check the compactness, the formulas for lambdas, if the section is taken from the steel manual, you can conservatively assume it as a compact section. Okay, sabihin natin compact na siya. Tapos yung pangalawa natin is yung lateral support, diba? Sabi sa problem, it is laterally supported all throughout the span. So hindi na natin kailangan i-compare. So no need for yung LB versus LP and LR. Hindi na natin kailangang gawin siya kasi sinabi sa problem laterally supported na. So ibig sabihin, kung pupunta ka doon sa step, sa procedure, okay, so based on procedure, on determination of MN, it will fall under, so yung, diba yung step 1, compactness check. Okay? Tapos yung case 2 is for compact section. So, a compact section naman siya. Tapos yung 2A is lateral supported. Tama ba? Okay. Balikan ko para makita nyo. Ito yung step, diba? So, ayun dito siya magfo-fall under sa 2A. Compact section, tapos lateral supported. So, anong MN dyan? So, ito yung MN niya. MN is equal to MP FYZ. So, yan na yung gagamitin natin. So, therefore, our MN is equal to MP is equal to FYZ. Okay, yung FY given naman sa problem, tama ba? Given naman kasi ito yung FY 50 KSI. Okay, so given yung FY, ano yung Z? Ito, sa manual, ito yung ZX. Okay, so given naman sa still manual yung ZX, so hindi ka na magsasolve ng ZX. O, edi yun na. So based from that, alam mo yung FY, alam mo yung ZX, edi may sagot ka rito sa MN. Okay, so tapos ka na. No? So i-substitute mo lang lahat yan sa equation. So you could know now if the phi MN is greater than the MU. So if greater than or equal, so safe siya. Okay, pagka less than, fail naman yung beam mo. So that is how to solve this type of problem, number 5, based on flexure. Okay? Okay. So let's have this sample problem number 6. Okay, for sample problem number 6 naman, we have a wide flange section, 14 by 90, tapos grade 60. So ito yung FY niya. And the beam is used as a simple beam with a span of 6 meters. So ito yung LB mo. Wala naman lateral support na nabanggit. Assume CB is equal to 1. Letter A, compute the nominal strength, flexural strength in kN meter. So ano yun? Nominal flexural strength, so that means MN. Tapos letter B, if the live load is twice the dead load, what is the maximum total service live load in kilonewton per meter that can be supported? So that means total service live load. What is the maximum total service live load? So that is live load ang hinahanap. So I look into the section properties. So yan yung properties. So check natin. So yan yung properties. So unang gagawin is check the compactness. How? I-check ko yung flange kung compact using the formula of lambda. Tapos ko-compare ko siya sa lambda limit, yung lambda p. Okay, so greater than siya sa lambda p, no? So i-check ko rin sa lambda r. This should be lambda r. So I stand corrected. So this should be lambda r. 21. So less than naman. So nasa pagitan siya ng lambda p tsaka lambda r. Kapag kayong lambda mo nasa pagitan ng lambda p tsaka lambda r, anong klaseng classification yon? Diba? Non-compact. Diba? Okay, so non-compact yung flange. How about for the web? O, yan yung lambda equation for the web. Tapos ito yung lambda limit. Tapos ito yung, as you can see, yung lambda natin is greater than or less than the lambda limit, yung lambda p. So therefore, we have a compact web. Non-compact yung flange, pero compact yung web. So pagka pinagsama mo sila, how would you describe the section? Non-compact section. Ayan. So non-compact section tayo. The next step is to check for the lateral, since non-compact siya, we check the FLB. No? Yung flange, yung solution ko naka-pattern siya dun sa procedure. No? So you just have to check na lang yung procedure. Okay, after compactness, so looking at the procedure, this will fall under 3.A. Diba? Yung procedure 1, procedure 2, yung procedure 2 kasi for compact eh. Procedure 3. So doon ako papasok sa procedure 3. Okay, pagka sa procedure 3 na tayo, non-compact flange, sabi doon, you need to check the flange local buckling. So yan yung formula for flange local buckling. Yung MP rito, sinolve ko muna. MP is equal to Fy Zx. O given naman yung Fy, given naman yung Zx from the section property, so makukuha mo yung MP. Tapos, i-substitute mo lahat yon dun sa formula na to. Okay, so direct substitution lang. So I got 1,012. Pero nung limit, di ba we have to check this with this limit, ang limit ko 1,065. So our MN is less than the limit. So ibig pasado naman siya sa limit. So, i-check natin yung LTB naman with LB 6 meters. 6 meters is the span of the beam. Okay, so ito yung lateral support condition, no? So, ito yung LP formula, direct substitution. Ito yung LR formula. Direct substitution lang naman yan, mahaba lang. Okay? So, you will find out that, ano ba? So, yan yung LR using those long formula. So, you will find out that our LB is in between LR at saka LP and LR. So therefore, it's partially supported. Pagka partially supported yung beam, ito ngayon yung formula na MN na gagamitin mo. Again, sinusundan ko lang yung procedure. So kaya nga mas maganda, habang dinidiscuss nyo to, hawak nyo yung formula. Para nakikita nyo kung saan ko kinukuha yung mga formula na to. So then direct substitution. So, ang makukuha mo kung MN dyan, 943 kilonewton meter. You just have to check with the limit again. Lagi ang limit natin yung MP. Okay? So, okay naman. So, pipiliin mo lang doon kung sino yung mas maliit. Okay? And mas maliit comes from this one, yung 943. Tapos, multiply mo siya ng resistance factor na P. Ayun na yung nominal. Ito na yung design strength mo. Okay? So, ito na yung design strength. Pero ang tanong yata kanina is nominal. So dapat ang final answer mo rito is walang 0.9 kasi nominal moment ang tanong. Okay? So pero pag ang tanong is design strength, i-multiply mo siya ng 0.9. Okay, letter B. Ano ra yung live load? So sabi sa problem, yung live load daw is twice the dead load. So ang gagawin mo lang rito is, okay, so the ultimate uniform load would be a combination of dead load at saka live load. Tapos yung live load, papalitan mo siya ng 2 dead load, twice dead load. So kaya ang magiging uniform load mo would be 4.4 dead load. Now, diba phi mn should be greater than or equal to mu. Okay? Tapos yung phi mn, nakuha na natin yung phi mn natin, yung 849.0078 greater than or equal to mu. Ang mu natin is the maximum moment. O, ano maximum moment sa uniform load simple beam? Diba? W L square over 8. Tapos yung W mo rito, ang lalagay mo dyan is yung 4.4 times the dead load. So, ibig sabihin, from there, you could solve for the dead load. And dead load dyan is, ayan, 42, this one. Ito yung dead load. Tapos times 2, yun yung live load. So, yan na yung pinakasagot mo. Okay? So, the maximum dead load would be 85. This one. And the maximum dead load would be 42. Pag tinanong kayo, what is the maximum total load? E di i-add mo lang yung service dead tsaka service live load. That would be the total load for this beam. Okay? So, that is how we analyze beam. So, ang mahaba lang, no? So, ito yung pinakamahaba talaga pagka sa beam. So, that is how we analyze flexural member. Okay? So, I hope you have learned out of this video presentation. Okay? So, thank you.